So now that we've learned a little bit about calculating probabilities, we wanted to get into different types of problem. So we know there's a distinction between or and end. We've seen that in sets. We've seen it in truth tables. An or event means one or the other will have to happen. An end means they both have to happen. So depending on what the problem states, we're going to have different ways to calculate the probabilities for these two types of words. So we're going to begin with or problems. So basically, we're going to be successful if at least one of the events occurs. We want this or this to happen. So let's look at an example. We want to determine the probability of rolling either an even number or a number greater than 4 on one roll of die. So we've got these two events going on. The first event is we could have an even number. So our successful even numbers would be 2, 4, and 6. The second possibility of us being successful is we get a number greater than 4. So the successful greater numbers are 5 and 6. So basically, we're successful on one of these even numbers, 2, 4, or 6, or also a 5 or 6. So as long as we roll a 2, 4, 5, or 6, we're going to consider ourselves successful. So basically, we have 4 out of 6 chances that we're going to roll an even number or a number greater than 4. So our probability would be 4 out of 6, which simplifies nicely to 2 over 3. So there's a 2/3 probability that we are going to be successful on this event. So there's a nice way to calculate these or probabilities. If you want the probability of A or B, you look at the probability of an event A being successful plus the probability of event B being successful, and then you subtract what's in common to the two. So if you kind of look at the last example, the probability that we're going to have event A be successful or we get an even number is a 50% chance. So you have 3 out of 6. Then the probability that event B is successful, which is the number greater than 4, is going to be 2 out of 6 or 1 out of 3. So you notice we have a little bit of overlap between these two. I've got this number 6 that appears in both of these categories. So that would be the probability of us having an even number and a number greater than 4. So we'd have to get rid of 1 out of 6 to account for this overlap. Okay? So sometimes it's very difficult when you have a lot of events going on that you can't clearly count every single individual item that's going to happen. But calculating this probability of the two events occurring simultaneously, we might be able to actually do. So let's look at some examples that we'll have to utilize this technique. So we want to figure out what's the probability that one card selected from a deck of playing cards. We want to determine the probability that the card we select is a jack or a spade. So this is where we run into that bit of an issue because spades, you don't want to list out every single one of them. There's 13 cards that are spades. I don't want to have to count this overlap and count every single individual card. So what we're going to do is we're going to utilize this formula we have. First thing is we want to look at the probability of getting a jack and the probability of getting a spade. So there's 4 jacks out of the 52 cards. So you have a 1 in 13 chance, or 4 out of 52, of getting a jack. For spades, there are 4 suits, so you have a 1 in 4 chance of getting a spade. Now what we're going to do is we're going to look at this instance. What's the probability we're going to have a jack and a spade? So for that, there's only one card that is a jack and a spade. So there's a 1 in 52 chance of you getting the jack of spades. So now that we have this, we can just utilize that formula. So the probability of a jack or a spade is going to equal the probability of a jack plus the probability of a spade minus the probability that both events are occurring. So the probability of a jack is 1 out of 13. the probability of a spade is 1 in 4. And then the probability of it being a jack and a spade is 1 out of 52. So the probability of it being a jack or a spade is 1 out of 13 plus 1 out of 4 minus 1 out of 52. So if you want this as a single fraction, it's probably going to be easier to just put everything in that 52. The 1 in 13 was the same thing as 4 out of 52, so you can utilize that. There are 13 cards out of 52 that are a spade, and then we want to get rid of that overlap, so the jack and a spade. So now that they all have the same denominator, we've got 4 plus 13 is 17, minus 1, the numerator becomes 16. And that does simplify. You don't necessarily need to, but you can divide top and bottom by 4. And that gives us a 4 in 13 chance of, if we pick one card, it's going to be a jack or spade. Okay? So let's try it again. Let's look at a club or a red card. So first thing we need is the probability of a club. Again, there's 4 suits, so you have a 1 in 4 chance of getting a club. For the probability of red, half the cards are red, half the cards are black. So you have a 1 out of 2 chance of picking a red card. Now we want to look at the probability of a club and a red card. And that's going to be 0. So the thing you have to remember about your standard deck of cards is clubs are black. So I can't possibly pick a card that is a club and it's going to be red simultaneously. Not possible. So when we go to look at this probability of a club or a red, it's going to be the probability of a club, which is 1/4, plus the probability of a red card, which is 1/2, plus the probability that it's a club and a red card. So we want to subtract that off, the probability of club and red, which is nothing in this case. So you get 1/4 plus 1/2 minus 0. So you have a 3 in 4 chance of drawing a card that's a club or a red. So in this specific case, when we had this particular event, when the probability of a club and a red card happening is nothing, so the probability of both events occurring is nothing, we say it's 2 events are mutually exclusive. So basically, 2 events are mutually exclusive if it's impossible for both events to occur simultaneously. So what that basically means is the probability of A and B occurring is 0. So it leads that or, the probability of A or B happening, to just be the probability of A plus the probability of B. Because you would subtract the end, but that's just 0. So it doesn't matter. So this piece disappears and you just add the 2 events together. So it's much nicer when the events are mutually exclusive, but it's not always the case. They might be able to occur. So just pay close attention to that. So the second type of problem we're going to take a look at are end problems. So to be successful in an end problem, both events have to occur. So if you want the probability of event A and event B occurring, you're going to take the probability of A and you're going to multiply it by the probability of B. So the one thing you have to be careful about is you're going to have to assume event A has already occurred when you go to calculate the probability of B, because it might potentially change what's happening there. So let's look at an example so you can kind of see what we mean. 2 cards are selected with replacement from a deck of cards. So we want to determine the probability that hearts are selected. So basically we're going to have 2 draws. The with replacement tells you I'm going to pull a card out of the deck, I'm going to take note of what it is, and then it's going to go straight back in. So if we look at that first draw, we want it to be successful, so we want to see what's the probability our first draw is a heart. So that would be 13 out of 52, or again, you have a 1 in 4 chance of getting a heart, because there's 4 suits. So now this card is going to go back in the deck. So when you look at the probability of the second draw, you still have the same options. You could potentially pick this card again. So you still have a 1 in 4 chance. So what that means is we've got the probabilities of each of these events, the first draw and the second draw. So if we want the probability that the first draw is a heart and the second draw is a heart, you multiply the probability of the first heart being drawn multiplied by the second heart being drawn. So each of them has a 1 in 4 chance. So you multiply 1 over 4 by 1 over 4. The probability that you're going to select 2 hearts in a row is 1 out of 16. Okay. Now if we change this slightly, this is where this note kind of comes into play, that we need to assume event A has already happened to calculate event B, because you want to be successful. So if I want to draw 2 hearts, I've got to assume my first card was a heart when I go to calculate the probability of this second draw. So we're going to still have 2 cards selected at random. We want to determine the probability that 2 hearts are selected. But now we're changing this word slightly. We're doing without replacement. So basically, I'm going to draw a card. I'm going to have to be successful, so the first card has to be a heart. Now that one is not getting put back in the deck. So when I go to calculate the probability the second one is a heart, I've got to take into consideration I've lost one of my options. So the first draw doesn't change. Probability that the first one is a heart is a 1 in 4 chance, or 13 out of 52. But now that card is removed. So not only do you have 1 less heart, you have 1 less card to draw from. So the second draw, instead of it being 13 out of 52, you've lost the first card, so you have 12 out of 51. So in the top, there's 1 less heart from that first draw. And then in the bottom, there's 1 less card as well. So you've removed that first heart. You no longer have 52 cards remaining, you have 51. So when we want the probability of selecting a heart and then another heart, we're going to multiply these 2 probabilities together. So the probability of the first one is a heart times the probability of the second is. So you have a 1 in 4 chance on the first draw, a 12 in 51 chance on the second draw. So the second one does simplify to 4 out of 17. So if you divide top and bottom by 3, and then nice stuff happens because these 4s cancel. So you have a 1 in 17 chance. So if you don't see that, you have to take the top and bottom. They're both divisible by 3. Okay? So what we can say from this is another special kind of terminology about 2 specific events. So events A and event B are called independent events if the occurrence of either event no way affects the probability of the other. In the prior example, the first event being successful does affect the probability of the second event. So we would say they're dependent. The second probability changed as a result of the first probability. So when we had this with replacement, these were independent. Because we put that card back, the second draw was in no way, shape, or form affected by the first draw. But in this one, because this second draw is affected, this is dependent on the first event. So my probability had to change to account for the fact that we had 1 less card. So let's try some more examples. We're going to have some colored envelopes that are shown below. So we have 3 pink ones, 2 blue, 1 green, and 1 purple. So if 2 events are selected at random with replacement, so again, that means I'm going to take this card, or I'm going to pick one out, see what it is, and then it's going to go right back into this pile, and I have the same chance of selecting it again. So we're going to do this twice. We want to determine the probability that neither envelopes are pink. So what that means, we want the probability of the first card is not pink and the second card is not pink. So we want to multiply the 2 together. We want the probability of no pink on the first draw times the probability of no pink on the second draw. So in this case, I've got these options for not getting a pink. So I have a 4 in 7 chance my first draw is not a pink. So I'm going to select one of these cards, figure out what it is, and then I'm going to put it right back in the pile. So you have a 4 in 7 chance for the first draw not being pink, and the same thing for the second because the card you picked is getting replaced. So when you multiply them together, the probability that neither envelope is pink is going to be 16 out of 49. Okay. When we change that and we want them both to be pink, now I've got these options here. So my first event, I could have a 3 in 7 chance. I'm going to pick that first pink envelope, hopefully, and then I'm going to put the envelope right back in, so I still have 3 options for the second draw as well. So the probability that I get a pink envelope the first time and a pink envelope the second time is the probability of each multiplied. And for both of them, you have a 3 in 7 chance. So we take 3 over 7, times it by 3 over 7. You have a 9 in 49 chance of drawing a pink and a pink. Okay. Now if we go through, that was with replacement. Now we're going to see what happens without replacement. So we're going to calculate the same probabilities, and we want first neither envelope are pink. But now I'm not going to replace the cards. So let's go back up to the top. So what we want is neither envelopes are pink. So in my first draw, I still have a 4 in 3 chance. But now I'm going to use up one of these cards. My second draw, I've only got 3 envelopes. So assume maybe we pick the purple, it doesn't really matter. Now I'm left with 1 less envelope and I only have 3 to pick from. So if we want neither envelope to be pink, we want the probability the first pick is not a pink, and then we want to multiply that by the probability the second one is not pink. So for the first one, you still have the same odds. There are 4 envelopes of the 7 that are not pink. So you have a 4 in 7 chance. But for the second pick, I've used one of these envelopes up. So this envelope is gone. I have 1, 2, 3, 4, 5, 6 remaining, and only 3 of them fit the criteria for us to be successful. Okay? So you have a 3 in 6 chance now of making the second envelope not be pink. So you used up one of the non-pink, which means you only have 3 left over, and there's 1 less envelope, so 6 are remaining. So 3 over 6 is 1/2. You can simplify a little bit because 2 goes into 4 2 times. So really you have a 2 in 7 chance that neither envelope is pink. So it's different than this with replacement. You had a 16 out of 49 chance. So we don't get the same probability. Okay. Now if we want to figure out what's the probability without replacement that both are pink, we still do the same thing. We want the probability that the first pick is pink, and we want to multiply that by the probability the second pick is pink. So when we go back up here, the first pick, you've got 3 envelopes out of 7. But Now I've used one of these up. So this envelope is gone. I have 6 remaining, and of those 6, 2 of them are pink, okay? So the probability, the first pick is pink, is still 3 out of 7. But for the second pick, you have 1 less pick, or 1 less pink card, and 1 less card overall, okay? So 1 pink is gone, and you only have 6 left. So 2 out of 3 is, or 2 out of 6 is still 1 over 3. The 3's cancel, and you have a 1 in 7 chance that both envelopes are pink.